students. So let's carry on from where we left last time. We're done till which point here? Charging by friction. We had completed charging by friction, right? So we had we had to do charging by friction. We had completed, right? Now let us see Coulomb's law for point charges. So see, till now we know that there are repulsive forces and there are attractive forces between the charges. Now we are going to we are going to find the values of the repulsive and the attractive forces. Like let us say you have plus q charge here and plus q charge here, right? And the distance between them is r. So what will happen if you have positive and positive charges? Will there be attraction or will there be repulsion between them? Positive and positive means there will be repulsion, right? So this will be repelled here and this will be repelled in this direction. On the contrary, if you have positive and negative charges and the distance between them is r, what will be there in between them? There will be attraction and repulsion. There it will be attraction, right? So we see that these forces act along what? Act along the line joining them, right? Here also these forces are acting along this dotted line, which is the line joining them. So forces are along the line joining the two charged particles. That is what the forces are. Here they are away from each other, I mean, because they are repulsive. Here, since they are unlike charges, they are attractive. Right? So take this down. Then we'll so see, force is a which quantity? Force is a vector quantity. So in vector quantity, which two things we have to talk about? We have to talk about the magnitude and the direction. So what have I spoken about till now? Till now I have spoken about direction of forces. Means I'm talking about what? I'm talking about direction of forces. Right? Direction. After this, what do you think I'm going to talk about? After direction, what am I going to talk about? You think? After this, I'm going to talk about magnitude, and that's precisely what we're doing in the next page, right? So once I've spoken about both the direction and the magnitude, I would have spoken about force in totality. That's what we are here to discuss, right? This electrical forces, this attractive and repulsive forces called electrostatic forces, have what magnitude, what direction? We are here to find that out, right? So take down the direction part, then I'll go to tell you the magnitude. So take a couple of minutes writing that down. Okay, so there was some official work and hence the interruption. Let's get back. So what we have done here, guys, we saw the direction of forces, right? Now after the direction of forces, what's the next thing we should do? Direction is done. Direction is done. है ना? After direction, what we will do? We will do the magnitude of force, right? After direction, let's check the magnitude. So magnitude of force is found to be proportional to mod q1 mod q2 divided by r square. And what is q1 and q2 here? This is, let's say, q1 and this is q2. This is q1, this is q2. So what are q1 and q2? q1 is charge on first object, right? And q2 is charge on second object, right? So force is proportional to the product of the magnitude of the charges, product of magnitude of charges, you can see magnitude, right, divided by square of the distance. R is what here? As you can see, R is the shortest distance between q1 and q2. And since the force is proportional, there has to be a constant of proportionality. So the constant of proportionality is K, and F comes out to be K q1 q2 divided by R square. Now K is a constant, right, and it's called Coulomb's constant. Its value is given as 9 into 10 to the power 9 Newton meter square by Coulomb square. And K is also equal to 1 divided by 4 pi epsilon naught. Now what is epsilon naught here? Epsilon naught is called the permittivity of free space or permittivity of vacuum, also called epsilon naught. And what is the value of epsilon naught? Value of epsilon naught is 8.85 into 10 raised to minus 12 Coulomb square divided by Newton meter square. So I can say that force is proportional to what? Force is proportional to product of q1 and q2 magnitude, and is inversely proportional to what? Inversely proportional to the square of distance, square of distance between charges. Right? And the next last part is, does the Coulomb law follows Newton's third law? So let me shift it a bit. So does the Coulomb law follows the Newton third law? And the answer is yes. Coulomb law does follow the Newton third law. So you can take this all down. Then we'll go ahead. Okay, so let's go ahead and let's see relative permittivity. So what is relative permittivity? Let's see. It is represented by epsilon r or epsilon rm or simply k, but we'll be using this as of now, epsilon rm, right? K is capital K actually. Here also we saw k, that was small k. Here also we are seeing k, but that is capital K, and it is represented for, it is used to represent relative permittivity. So let us see what is relative permittivity. First of all, it's a ratio of permittivities. Relative permittivity is ratio of permittivity, as you can see, epsilon rm. Here m means medium. So relative permittivity of a medium, relative permittivity of a medium is the ratio of permittivities. This is permittivity of medium. This is permittivity of free space, right? So relative permittivity of a medium is permittivity of medium divided by permittivity of free space ratio. And epsilon m is the permittivity of the medium, and epsilon naught is the permittivity of free space. And epsilon r or epsilon rm, as I am calling it, is greater than or equal to which value? 1. It's greater than or equal to 1. Now I have to find out what will be the epsilon r of vacuum. That means we are going to find out relative permittivity of vacuum. And what is the permittivity of vacuum? Two questions are there. So first you take this down, then I'll address the last two questions separately. So understood relative permittivity, as I said, relative permittivity is represented as ERM, epsilon Rm, which is epsilon m divided by epsilon naught. Epsilon m is the permittivity of the medium, epsilon naught is the permittivity of free space. And you take the ratio, what you get is epsilon Rm, which is the relative permittivity of a medium, which is permittivity of the medium divided by permittivity of free space. And also, what can you say about the dimension? is relative permittivity, is it a dimensionless and a unitless quantity? The answer is true. Why relative permittivity is dimensionless and unitless? What is the reason? Because as you know, ERM is ratio of what? It's a ratio of permittivities only, right? Permittivity of medium and permittivity of free space. It's a ratio of mediums. So if you take ratio of two quantities, of course there will be no unit left. So it will be a unitless quantity and a dimensionless quantity, both. Take this down. Right, let's go ahead. Okay, we had to see what is the epsilon r of vacuum. So let us check it here. Epsilon rm can be written as epsilon m by epsilon naught. That's the formula we just saw. And I want to find for vacuum. So my medium here is vacuum, medium is vacuum. So that is epsilon of vacuum divided by epsilon naught. And what is epsilon of vacuum? What is the permittivity of vacuum? What indeed? What was it? See? Epsilon naught. Permittivity of free space or vacuum is epsilon naught. So epsilon of vacuum is coming out to be epsilon naught divided by epsilon naught, which is equal to 1. So epsilon Rm of vacuum is 1. Then similarly, epsilon R of water. Can you guess how much it is? For water it is 81. So different mediums have different value of epsilon Rm. Take this down. Now let us see net force on two charges. So what is the force on Q1 and Q2? F is given as, they're kept in vacuum. So what is the formula? 1 divided by 4 pi epsilon naught into mod Q1 into mod of Q2. That is the force. Now if they are not in a vacuum, then what is the formula given as? 1 divided by 4 pi epsilon naught, and a new term comes, which is epsilon Rm, and the rest of the terms are as it is, mod Q1 mod Q2 by R square. Right. So you see, the force in the medium depends on this quantity also, right? And value of epsilon Rm depends on the medium. So force, which force exactly are we talking about? Electrostatic force. Becomes medium dependent or independent? Becomes medium dependent. Got it? And thanks to which quantity? Why the dependence is there? Thanks to presence of epsilon Rm. because this is medium dependent. Take this down. Right, so let's go ahead and see what are conservative forces. So conservative forces, what are conservative forces? Work done by conservative forces in any closed loop is zero. Closed loop means what? Means start from one point, go around, come back to the same point, means initial and final points are same. If work done by such a force is zero, it is called conservative force. Right? So conservative force means work done by the force is zero. Right? Now, this another way for talking about conservative forces. Okay, first take this down, and I think time's up anyway. So we'll do the next part next time. So I hope this one is clear. If work done by the force in a closed loop. Closed loop means start and end points are same, and if that's the case, work done. If the force is conservative, work done will be 0. Right? Take this one.